class 10 circles. Whatever we learned in 9th class, we just go through very quickly. The definition of a circle: circle is a collection of all points in a plane which are at a constant distance from a fixed point. That fixed point is called center, and the constant distance from the center is called radius. A line segment joining any two points on the circle is called a chord, and a chord passing through the center of the circle is called a diameter, and it is the longest chord, of course, you know. This much is sufficient for us about the definitions, etc. Now let us talk about a circle and a line. Suppose a line and a circle are taken. There are three cases. In case 1, the circle and line may not touch, may not intersect each other. Therefore, they are called completely non-intersecting. They are called non-intersecting line and circle. Here like this: 1, 0. 10, you remember, 10, the number 10 will tell you about non-intersecting line and circle. The second case, the line may be falling on the circle, intersecting the circle at two different places. In that case, we call the circle, the line is a secant to the circle. This line PQ is a secant to the circle. That means it's a chord actually extended on either side. Chord is only a line segment. If that chord is extended on either side, it becomes a secant. Suppose this secant is brought like this. The secant, another case of the line and circle can be like this. Both the line and circle may touch at a particular point A. Okay, so in the second case, we call this one as secant. These are non-intersecting. I need not tell you about that. This is secant. And please don't confuse between this secant and secant we learned in trigonometry. Okay, this is a line segment which is intersecting a circle at two different points, two distinct points. Whereas PQ is touching or intersecting the circle at exactly one point. Therefore, this one is called tangent. What is this called?
Tangent.
Tangent. This tangent and circle, they have only one point in common. Tangent and circle have only one point in common, and that point is called point of contact. The point where a tangent touches the circle is called point of contact. POINT, point of contact. Point of contact means touch actually. Okay, point of contact. So we learned about line and a circle. So if a line and circle are taken, they may not be intersecting at all, non-intersecting type, or sometimes the line may fall on the circle, intersecting the circle at 2 points, that is called a secant. Tangent is such a line where it touches the circle at exactly one point or intersect the circle at exactly one point. This point is called point of contact. And secant, if the secant is both the points are merging like this, it becomes a special case of a tangent. Okay. Now let us talk more about this tangent, etc. And in theorem 1, the tangent at any point of a circle is perpendicular to the radius through the point of contact. The tangent at any point of a circle is perpendicular to the radius through the point of contact. This is the first theorem in this chapter. Let's learn this. Here is the circle and xy is the tangent, and we have drawn a radius OP to the through point P, the point of contact here, and we have to prove that OP is perpendicular to this tangent xy. Tangent is a line which is touching the circle, that much you remember. And we can have a number of tangents to a particular circle, because circle is a collection of many points. So at every point of the circle we can have a tangent. Right. Now a circle with center O is given with xy tangent at point of contact P. Now we have to prove that OP is perpendicular to xy. We have to prove that. Let us now take a point Q on xy and join this one, connect O and Q, and O passes through the circle of course, and OQ line segment passes through this one like this and intersect the circle at R, this point. That means OR is equal to radius of the circle, is it not? That is the distance between any point on the circle and the center, therefore it is radius. So OP and OR are equal. That means OQ is greater than OR. We can understand that. OQ is greater than OR. Therefore it is greater than OP also. OQ is greater than OP also. Right? And hence OP is the smallest line that connects xy. OP is the smallest line connecting O and the line. And it can be the same case if you take another line also, it happens the same. Suppose I choose another point, say S here, and join OS like this, then it intersects the circle at say another point T. Then OT is equal to radius and OS is greater than OT. OT and OP are equal, so OS is greater than OP. Again OP will become the smallest line segment connecting the point O, the center of the circle, and the line segment, that is the tangent. Now let me erase all these things. That's what I want to do. So now we have proved that OP is the smallest line segment connecting the center of the circle, or OP is the radius. OP is the smallest, this one. So OP is the radius also. Therefore radius through the point of contact is perpendicular to the tangent. That is what we have now proved. OP is the smallest line that is perpendicular, and OP is perpendicular to xy. Okay, did you understand this theorem? Very simple. Only two steps here in this. OQ you have to draw. Say that is greater than OP. And you can claim that it is the same with any other point on the circle. Okay, it's a simple theorem, important, maybe for 3 marks or 2 marks. So be ready. You may get it in the final exam. Next one, tangents to a circle. Suppose a circle is there, and a point is in the interior of the circle. Let us take the case here, circle, and a point, this is the center of the circle. Another point P we have here in the interior. Can you draw a line which is a tangent to the circle passing through P? Can you have any tangent? Let us draw a line like this. It is passing through this one. No, it is intersecting the circle at 2 different points. So there we cannot draw any tangent. There is no tangent to a circle passing through a point lying inside means in the interior. Okay, this is first case. Case 2, there is only one tangent to a circle passing through a point lying on the circle. So through one point we can have only one tangent. So many tangents can be, so many lines can pass through, but all those cannot be perpendicular to this particular radius here. Only one can be perpendicular, all others cannot. So only one tangent we can have passing through a point lying on the circle. The third case, circle and a point which is in the exterior or outside, lying outside the circle, say it is x here, point x. Then from here we can have 2 tangents to the circle, say like this. One is that this way, another is this way. See, 2 tangents we can draw. So xa is one, bx is another. So two tangents can be drawn to a circle from a point which is lying outside the circle. And remember, tangent is a line, not a line segment, of course, a line. So AX is a line where A and X are points on that. It's a point here. The distance between a point and the point of contact here, the distance, if a tangent is taken, the distance between a point and the point of contact is taken as length of the tangent. What is that called? Length of the tangent. Now we shall have another theorem on length of tangent. This is also very important and very easy. Prove that the lengths of tangents drawn from an external point to a circle are equal. This is the one. Simple. Let us take a circle with center O and a point P outside the external point, that is outside the circle, and we have two tangents. Now T and S are the points of contact. Therefore PT is the length of tangent PT here, PT, and PS are the lengths of tangents. We have to prove that PT equal to PS. So for this, join PO and TO and SO. All these points we are joining. Now you have understood already because they are dotted lines. PT, PS are the tangents from an external point P to the circle with center O. What to be proved? PT equal to PS we have to prove. Construction, join O to P, T and S, of course. Right. Now we have to give the proof. Now by joining the points P, T and S to O, we have two triangles here, and triangle OTP, this one here OTP, and triangle OSP. Two triangles here, these two triangles. In these two triangles, what are all common and what are all equal? Let us understand. OT equal to OS because these two are radii of the circle, right? Then OP is a common side. OP is a common side, that is also equal for both. So two sides are common. One more. Let us see. Angle OTP. In triangle OTP, angle OTP is equal to angle OSP in triangle OSP. So these two are right angles. Why right angles? Because a tangent is perpendicular to the radius through the point of contact. At T, PT is perpendicular to OT. At S, PS is perpendicular to OS because OS is the radius. So each is equal to 90 degrees. This is a right angle, and opposite side to right angle is called hypotenuse. This is hypotenuse OP, and this is a side. So by RHS congruence criterion, these two triangles are congruent to each other. OTP is congruent to OSP. Next, automatically the proof follows here. What is that? These PT and PS are the corresponding sides of congruent triangles, therefore they are equal. Got it? Did you understand this proof, children?
Sir.
It is not at all difficult, only 4 lines. 4 lines, 5 lines in the proof, I think. 1, 2, 3, 4, 5 lines in the proof. That's all. And simple logic also. Logic through the congruency of triangles. Okay. These two theorems are important from this lesson, and we will go through some examples and exercise problems from this lesson now. Shall I move on?
Yes, sir.
Okay. This is exercise 10.1. How many tangents can a circle have? Can anybody tell the answer?
Infinitely many.
Very good. A circle can have infinite number of tangents, infinitely many tangents. And fill in the blanks here. A tangent to a circle intersects in dash points. You all wait, let us see the complete question first. A line intersecting a circle in 2 points is called dash. A circle can have dash parallel tangents at the most. The common point of a tangent to a circle and the circle is called dash. Right, first one. Tangent to a circle intersects in how
One
many
point.
points?
1 point, sir.
1 point, sir.
Very good. That's right. It is exactly 1 point. Then, okay, I have already taken the answer here. Line intersecting a circle in 2 points is called a secant. A circle can have how many parallel
Two
tangents at
parallel
the most?
2
tangents.
parallel
Two parallels.
tangents.
Two only. Only two. Because only two lines out of all the lines can be parallel. Then the common point is called?
Point of contact.
Point of contact.
Very good. Super. Point of contact. That's nice. That's nice. This is the second question. And then third question, we have to apply our logic here. Here, a tangent PQ, okay, let me do this one. A tangent PQ at a point P of a circle of radius 5 centimeters. Say this is the circle of radius 5 centimeters. 5 centimeters radius. This is 5 centimeters. Say this is O is the center of the circle, and PQ at a point P they said. So this is point P now, point P, and PQ is the tangent here. Q is the other point. We have to find what is OQ is given already. OQ is given already. That is 12, and of course this is a right angle because tangent through the tangent is perpendicular to the radius through the point of contact. We need to find the length PQ now, length of tangent PQ. How to find this? Simple. You have to apply Pythagoras theorem because it's a right triangle, two sides are known to us. So PQ is equal to square root of OQ, that is hypotenuse square, minus other side OP square. 12 square minus 5 square, 144 minus 25, and we got 119 as the length of side, length of the length of PQ. This is square root 119. Did you understand this one?
Yes, sir.
So like this, Pythagoras theorem can be applied to find the lengths of tangents. Now question number 4 in that exercise and the last one in that exercise. Draw a circle and two lines parallel to the given line such that one is a tangent and other is a secant. It's a simple activity. We draw a circle and we take a line L here, and this line and this one, two more lines we have drawn, which is a tangent. One is a tangent, another is a secant. So with this we come to the end of this lesson today.